Now, starting with the seed, we are going to be tracing through every operation in this computation graph. So for example, tracing through the product means I'm simply applying the chain rule. So the derivative of x1 times x2, the output of this product with respect to anything, in this case, sorry, x2, in this case, x2, right, is going to be equal to the partial derivative of the product, which is basically x1 times partial x2 to x2, right, plus x2 times partial x1 to x2. So this we already said is equal to 0, and this we already said is equal to 1. So the end result is going to be the sensitivity of the product with respect to x2 is equal to x1. So following this procedure here. I mean, this procedure actually works no matter what the inputs of the product is. So if the product happens in the first stage of this computation or happens somewhere in the depth of the computation, it doesn't matter. We follow essentially the same rule here for computing the derivative of the output of the product. Similar things happens in this sign operation. The derivative of the output of the sign operation is simply equal to the partial derivative of the sign operation, which is cosine of W1, times the derivative of the input of the sign, which is this formula here, right? W4 dot is really the derivative of the output of the sign, right? It is equal to the derivative of the input of the sign, W1 dot, times the partial derivative of the sign operation. Okay, so with the derivative of the output of these two first stage operations computed, we then propagate the derivative forward. Now we know the derivative of the inputs of the plus. The task is to now compute the derivative of the output of the plus. Again, we're going to be using the partial derivative of the plus operator. And in this case, the partial derivative of the plus operator with respect to both of inputs are 1. So the output has a derivative that is equal to 1 times the first input plus 1 times the second input, right? That way we have already computed the derivative of the output, the final output, with respect to the quantity we want to differentiate with respect to. That's the forward propagation procedure. And as you can see, the procedure can be applied algorithmically. At every stage, we can just store the partial derivative of every simple operator, right? I mean, we have to know the derivative of these simple operators. For sine, it's going to be cosine. For multiplication, it's the derivative of one operand multiplied with the value of the other operand plus the derivative of the other operand multiplied by the first operand. And essentially, you actually have a small library of what is the partial derivative of these various operators. And you just keep applying this library of partial derivatives and propagate the derivative forward, starting from the derivative of the inputs, ultimately to the derivative of the output, which is what we want. That's forward propagation. And another way to compute the derivative is backward propagation. And why do we want backward propagation? I mean, the reason is that it has a distinct advantage with respect to both forward propagation and finite difference. Go back to the forward propagation case. Once we have completed the forward propagation, we have computed derivative of the output with respect to one of these design variables. If we want to compute derivative with respect to both design variables, we have to use two different set of seeds, right? We have to seed our W1, W2 to 0, 1. If we want to differentiate with respect to x2, we have to seed the derivatives to 1 and 0, as opposed to 0 and 1, if we want to differentiate with respect to the first input, x1. So the whole computation has to repeat multiple times if we want to obtain derivatives with respect to multiple input parameters.